In the last section of this part, we'll look at the primal dual schema, which is a way to use the duality and the theory of linear programming, but without invoking a black box solver in your algorithm itself. At least that's usually how it ends up working. And so it's both beautiful because it often gives you insights into the problem itself and leads to more efficient solutions or more efficient approximation algorithms in terms of their actual running time. So far, we've been mostly focused on the approximation ratio, and the algorithms range from simple greedy heuristics to let's start by solving a full LP and then rounding something. So you could say it were essentially ad hoc methods, maybe in hindsight justified with arguments from linear programming. And if they rely on a solver, it can be expensive. There is a way to use duality slightly more directly. And I would say against all odds, the kind of best solution often comes from the complementary slackness conditions, which are precisely the conditions where I said, hold on, these are true for linear programs, but they're not true for integer linear programs, at least the one direction. If you have some solutions, some pair of primal dual solutions that satisfy them, then great. They're simultaneously optimal and with equal objective value, but most hard problems will not do you the favor of satisfying these. And so they seem to be of little use, but indeed you can make them useful in the following sense. You can consider some relaxed version of the complementary slackness conditions, and I'll show you in a second more concretely what that means. And then we can try to somehow maintain a pair of solutions that satisfy these relaxed complementary slackness conditions. Curiously though, normally the complementary slackness conditions start with let x and y be a primal dual feasible pair of values, and then if these conditions are satisfied, then that's an if and only if the two are optimal. Here we're going to use the complementary slackness conditions, the relaxed versions, and it turns out the relaxed versions don't imply feasibility anymore. So we're working with solutions that are satisfying these modified CSC conditions, but are not necessarily feasible. You'll see how this makes a lot of sense in the example, but still the general, I want to describe the general schema because it is more applicable than just to the example problems. So the primal solution will keep integral, but it may not be feasible initially. For the dual, we don't care about integrality, but we want to keep it feasible. And then we use the complementary slackness conditions to guide us where to make changes. And so we're trying to make x more feasible, and that means we're going to make y not satisfy the complementary slackness conditions, and we let those guide us how to adjust things. Okay, it's a bit vague. The cool thing about this general theme is no matter how you do it in details, if you maintain this dually feasible y, that's always going to be a certificate for how far away from optimum your solution x is in the end. You have to keep going until x becomes feasible, otherwise it's nothing, it's no solution at all. But once x becomes feasible, if you've maintained a dually feasible y, then that gives you a bound on the optimum. And so oftentimes you can a priori guarantee that you're getting a certain approximation ratio. Okay, let's see this in a bit more concrete. First of all, these are the complementary slackness conditions as we had them before. So for standard LPs. And again, standard LPs, just to have them here again, are these two. And so if you look at what the complementary slackness conditions say, they're essentially pairing a variable in one problem to a constraint in the other problem. And remember, these are, from the way we dualize, this is very natural that you would get this pairing. Because a variable in the dual, let's start with this, a yi here, is essentially the multiplier we put on the constraint, on the ith constraint in the primal, and vice versa, because, okay, I never said this, but if you take a problem and dualize it, and dualize the dual again, you get back the primal. That's something I never said, but it is true, though, nevertheless. Okay, but it's natural in this case, so y was the multiplier for the ith constraint in the primal. I think I'm always going to denote this as the primal, this as the dual. So it would help if the p wouldn't look like a d. And vice versa, so x can be seen as the multiplier of the jth dual constraint. And here, this is just one of the constraints where you replace the greater or lesser equal with equality. Okay, that's complementary slackness. And the conditions say, well, there's two options how a solution can be tight and optimal. Either the multiplier I'm giving to the constraint in the primal is 0, so I'm gonna kill that constraint, or it's gonna be satisfied with equality. And if you think, well, you can tie it back to extreme points, and so maybe I'm not gonna get into the polyhedral theory again. But clearly, these constraints are a stricter version of the constraints in the original problem. You replace the lesser equal with equality, so they still imply the original constraint. They're just more strict. Now, the relaxed versions that we'll look at, they replace this strict equality here with a bit of slack. So I really wish we would have those on the next slide as well. There's two parameters, alpha and beta. So for the two primal, for the two pairs of constraints, we allow a different fudge factor. For the first one, we take this constraint that used to be equal to c and say it's at most c, but at least c divided alpha. Okay? And so you see that's still somewhat still refines this constraint here, but leaves a bit of slack, so it doesn't require it with equality, it requires it with a slack of alpha. For the second part, we also have that this, so that's a b, not a 0. Here also you have the constraint ax greater equal b, but we don't require equality anymore, just not too much, too far away from b, not too much bigger. Okay. And the core of the primal dual schema is if you have x and y, a pair of primal dual feasible solutions, and this can mean in an ILP or in an LP. Both works same way now. Whatever problems you're looking at. If they satisfy these alpha beta relaxed complementary slackness conditions, then you get a quantified version of weak duality if you want. The cost of the CTX is at most alpha times beta times this dual cost. Okay? So weak duality would be, strong duality would be equal. And weak duality would mean the minimization problem is greater or equal this. And now we're getting something in the opposite direction, so we sandwich CTX between BTY and alpha beta BTY. The proof for this is just from computing from the definitions. It's relatively boring. You take CDX. Now you're going to use on C your complementary slackness condition, this part, if you multiply by a, then you get this a alpha times, sorry, multiply by alpha, you get alpha aty for c, and the x is where it is. Then you expand the transpose, then you have ax, which you can just bound again with this one by b beta times b. We replace that, and then you just swap things around. Beta is a scalar, so you can move it to the beginning. Okay. Trivial proof, but the point is, if you can somehow make these relaxed complementary slackness conditions hold until you get some feasible solution, then you get a guarantee for the approximation ratio. Cool. Let's finally see this in action. If you look at our set cover LP and dual LP, you get the complementary slackness conditions like this. Either the variables is 0 as always, and then you have the dual constraint. We can't pack, I think this was always an E. Doesn't matter, but yeah. So you kind of can't, you're packing, so the true complementary slackness conditions is you pack exactly as much as the capacity of that set. And for the primal constraint, you cover exactly with 1. In general, this will not be possible to fulfill with integral solutions. So we relax it and we pick alpha as 1, and we pick beta to be f, the frequency of the element, the maximal frequency. And in this case, it just makes this second part trivial, in the sense that all we're asking for here now is if you sum up all the sets where an element E occurs in its variable, it should be at most f. But if you keep the x chase below 1, that's always going to be satisfied, because we have at most f sets where this occurs in. So it's kind of, we're making that second condition completely trivial. But hey, that's fine. Trivial conditions are easier to satisfy. And in the end, we're going to aim for a factor f approximation, right? Alpha times beta is just f here. So that's what's going to pop out. And then you can do the following cute algorithm. That's the primal dual set cover approximation. F is the global frequency, so the maximum number of sets that any element occurs in. We initialize our two solutions, x and y, with the all 0 vector. And t will be the elements, part of the universe that we still have to cover. And as long as some elements are not covered, we take some element. And now there's no greedy heuristic or something like that. But instead, we take the dual variable, the ye, and we're trying to pack more of that element. And so if you do that, there's going to be some point where, at least for some set, you're going to hit this this constraint with equality. Right? So the ye's, you can make them bigger. But at some point, you're going to have, the constraint was less or equal. At some point, it will be exactly equal for some sets. Okay? You keep doing, for the single variable, you increase it until you hit, for some sets, the boundary, the threshold. And then you look at all those sets where this is now satisfied with equality. So this is the first part of the complementary slackness condition. So if this part is satisfied, that means we no longer need x to stay at 0. Remember, we initialize x and y all to 0, which means I really wish we had these on the slide. This is stupid. Let's do that. Chunk. Yep. Maybe here. So making sure these are always satisfied is trivial if you say x and y are all 0. Then the first part always satisfies the whole thing. But then we don't make any progress towards a feasible x. So we take one of the y's, we make sure that we're trying to satisfy the second part by raising y. And once it hits exactly the upper bound, we're free to make xj to set that to 1. And that's what we're doing, right? We set xj to 1, we remove all the elements from T that are now covered by Sj, and then we repeat. So in a way, it's still a kind of greedy algorithm, but the greed is now with respect to this dual variable. And that way it's a bit more careful than the original greedy. It's an F approximation, not just this Hn. Well, okay, they're, I guess, in general incomparable. So we keep doing this until there's no element left that's not covered. And so this is an F approximation. And there's not much to show. The key thing here is that the proof becomes much easier with this setup. The algorithm only terminates when X encodes a set cover. Otherwise, there would be some elements in T left. So at the end, X is primally feasible. And when we have some element that is included, we only include it when at the time this the dual constraint was satisfied with equality. That's this CSC1, as I called it in the proof. So if that's satisfied with equality now, we're actually never going to change it. That only depends on the elements ye for elements in this set, and we only ever change ye's for elements that are still in T, but we've removed all the elements from Sj. So this was true now and is not going to be modified. So we'll keep that at equality. And so that means our xy pair at the end satisfy these 1F relaxed complementary slackness conditions. And so that's all we really need, because then we can use the previous lemma for getting the approximation guarantee. And here it's a factor F. I guess we would need to argue that y is feasible, but we keep y feasible initially and throughout. Unlike for the primal, the dual problem here, yeah, this bumped around weirdly. For the dual problem, setting all y's to 0 is a feasible solution. And so it's initially feasible. We never bump it above the capacity, so it remains feasible. And so that's a pretty slick and short proof of this fact. And a similar kind of, you can apply the same thinking to other problems. It's much more versatile now if you think about it, because all we need is really some LP or ILP representation of the problem. And then much of what we're done here is guided from the ILP and doesn't need problem-specific insight. Apart from which alpha beta to pick, that's the only part. And that is it for approximations. We've seen a lot of small examples, so I wanted to list the different design patterns again. There were 2 based on rounding. Either you do some simple thresholding, or you do some randomization and coupon collecting. And we've seen today, to complement those 2 methods that use the duality theory of LPs, either to just analyze an algorithm that we've somehow come up without, or to specifically, from first principles, start with the primal and dual problems and devise an algorithm from there. That brings me to the end of the approximation chapter, and also the end of the material for this term. So thanks for staying till the end, and we'll see each other for the fun lecture for enrichment next week.